Hey guys, welcome back. I wanted to do a video on the Overshoot focuser backlash compensation and possibly making use of this idea within Astrophotography tool. So as part of this video, I want to at least touch on the idea of why do we need to compensate for focuser backlash for those of you who might not be doing that at this stage. The comparison between the absolute, call it the obvious, versus the overshoot, call it the clever, methods of focuser backlash compensation. And how does the overshoot method work? I want to show a little simulation, pseudo animation of how the overshoot method of focuser backlash compensation works. And then how can we use the overshoot method? Can we use, in fact, the overshoot method of focuser backlash compensation within Astrophotography tool? And it's just been included within Nina version 110 nightly build 81. And the thing that prompted this little video on my part is another video. Believe it or not only do I make videos, but I actually watch YouTube videos. And Queeve, the so-called and improperly named lazy geek in Japan, came up with this video that captured my attention quite quickly because, as you know, I have a somewhat tame obsession with focusing of late. He came up with a video discussing the introduction of this overshoot method of focuser backlash compensation within Nina. And so any title that says focusing just got better in Nina is something that obviously attracted my attention right off the bat, as I am feeling the gravitational pull of Nina primarily because of the autofocusing capability that it has. So this title caught my attention. And for those of you who haven't caught on to Queeve, I suggest you go check out his channel. He's got a lot of good Nina content, but there's also some good content just on equipment and procedures, processing. He does a great job of making some good, offering some good technical content in an entertaining way. With me, you just get the technical content, not so much the entertainment. But anyway, check out his channel because I think there's some good stuff there. Why do we need to account for focuser backlash? And in a minute, we're going to show some simulations of what I mean. What is backlash from a mechanical perspective, and how is it working? But just take my word for it at this stage. You've seen or perhaps experienced curves like this before, where we have the half flux diameter or the full width at half maximum of a star field or single star plotted versus focuser position. And so what happens during an autofocus procedure is we take the focuser and for example in this case we move it out of focus in the outward direction, say. So we start up in this focuser position, we take a picture, and we get the half flux diameter, and then we move in at regular increments of focuser position, taking pictures and recording the half flux diameter at each position, and therefore being able to create this plot of red dots, after which we fit a curve, whether it's the intersecting lines curve or a parabolic fit, or as in this case, and my personal favorite is the hyperbolic curve fit. We fit this curve to the data, and then based on that curve and the minimum, it tells us where the optimum focus position should be. Here's the critical point. We've been here and we've taken inward steps all along, so there's no backlash once we start moving along this curve and collecting data. And now, for the first time, as we want to move back to the optimum focus position, we're having to change direction of the focuser, and that's when you experience backlash. So the autofocus routines in general rely on reversing direction to find the optimum focus point. And if you have some backlash left over in your system, what you'll find is that you'll command a movement over this many steps to get back to the optimum position. But if you still have some residual backlash, or if you haven't taken care of backlash, what you'll find is that some of those steps are just taken up with the focuser moving, but not the sensor, because the gear train between the focuser and the gear train associated or connected directly with the imaging sensor haven't been in contact because of backlash. And as a result, you may command a move back to here, and your focuser moves back there, but not the sensor. The sensor may be back in here somewhere, leaving you with an out of focus or higher than desired have flex diameter. So you've got to take care of backlash in order to make this autofocus routine make sense and to be effective. That's the critical issue. Now, it turns out, unbeknownst to me until I saw the video I just mentioned, I only thought there was one way to do this, the so-called absolute method of backlash compensation, when in fact what has been going on in Sequence Generator Pro is the overshoot method of backlash compensation, and now Nina has incorporated that. And so I want to take this opportunity to figure out, can we, devotees of astrophotography tool, make use of overshoot method of focuser backlash compensation. I put out a video sometime back. In fact, I've had a couple of videos on this. One associated with my Celestron focuser and another one associated with the Pegasus Astro Focus Cube 2. The one with the Focus Cube 2 is documented in the video titled Measuring Focuser Backlash and Filter Offsets with a Batenoff Mask. Okay, now the reason I did that is many of these manufacturers will say to measure backlash, what you do is you make sure that you're, for example, fully engaged in an outward, with the gears are engaged for outward motion, and then you start moving the gears back the other direction until you can see the knob on the OTA side of the focuser move. Well, all right, what if you don't have a refractor and there's no knob, and the only thing that's moving if you have a Schmidt Cassegrain, for example, is the primary mirror inside the tube that you can't see? So some of these methods that the manufacturers of these focusers give you tend to be a bit simplistic. I created a video, and the procedure I've used for both of my focusers is based on actual focus data, in this case using the Batenoff mask. And as you can see what I'm doing up here, I have a Batenoff mask on. This is the window from Astrophotography tool. I'm using Batenoff grabber in conjunction with the image that I'm showing here with Astrophotography tool. And up here in this corner right here is the so-called focus error in the number of pixels. And so what I do is start outside of focus. I take an image, record the Batenoff error, move the focuser in, get the Batenoff focus error, and so all the way through the critical focus zone where it goes through zero focus error. And as soon as I'm certain that I'm outside or well beyond that critical focus zone, then I start moving the focuser back in along now what will ultimately be a different line, but moving it back in, and again recording the focus error. And now the difference in focuser steps from where the inward motion and the outward motion cross the critical focus zone, that's your actual backlash. And I think this is a much more accurate way of measuring actual backlash. But what is new to Nina and what is new to me is the overshoot method of backlash compensation, where we don't have to have this accurate assessment of the focuser backlash. And that's why I wanted to make this video and talk about a little bit. There are basically two methods of backlash compensation. One that I just described with the in the previous chart is the absolute method of backlash compensation. The idea here is that you compensate for the actual backlash, but you've got to measure the actual backlash whenever the focuser direction is reversed. So if you're set to move in and you want to move the focuser back, then the backlash setting that you have will wind the focuser back so that the gears of the focuser and the gears of the OTA side of the focuser become just in contact, and then your commanded step is implemented in addition to that backlash compensation step. Now, the advantages of this approach are that it does in fact compensate for focuser backlash, but only if your backlash settings are accurate. You can't overestimate or underestimate the backlash, otherwise you'll be off by that amount. Now, if you're off by just a small amount and still within the critical focus zone, that's okay. We're not talking about total precision here. We're talking about being fairly accurate. Also, the advantage of the absolute method is that if you happen to have a mechanical system that has a different backlash setting for inwards motion from the backlash setting for outwards motion, you can account for that using this absolute method of backlash compensation. The thing is, this is, I suspect, fairly rare. The second thing is, I consider an advantage is that it requires a minimum amount of focuser movement. Why is that important? Well, it depends. I've noticed, particularly in using my refractor, when I make focuser changes, the torque applied to the dovetail plate and the OTA does translate into some shift of the RA or deck axis that moves the star. That can be problematic if that motion is significant. In some cases, it's fairly minor and you don't have to worry about it, but in other cases, it might be something worth considering. So I don't think this undermines the total use of, or at least trying out of, the overshoot method of focuser backlash compensation, but it is something worth considering. Now, the disadvantage of the absolute method of backlash compensation is that it does require an accurate measurement of the backlash, and that's why if you feel like you need to go down that path, I might recommend the methodology that I presented and discussed in that video that I showed on the previous slide. There are some real advantages to using the overshoot method of backlash compensation. First of all, the overshoot method of backlash compensation starts off with your system in contact for either inward motion or outward motion, so that when you make a focus change in the opposite direction, that's the direction that you have to compensate for backlash. Focuser motion in the other direction, where the gears are already in contact, there is no backlash, and it's just a direct ask for a step, get a step kind of arrangement. The advantage of this system, of this approach, as we'll discuss even in more detail going forward, is that it does not require accurate backlash measurement. If you have an idea of how many steps of backlash there are in your focuser system, then that's fine. Just an idea, and now double that estimate or multiply it by 50%, increase it by 50%. And just all you need to make sure is that you overestimate the amount of backlash that's actually in your system. The disadvantage of the overshoot method is that it is going to make the assumption that the backlash is the same in both directions. I don't think that's a big disadvantage. That's probably the case anyway, so I don't think that's a big thing. The other possible disadvantage, depending on your setup, is that there's going to be more motion of the focuser with this overshoot method than it would with the absolute method, which could cause some issues. For example, with my Celestron focuser, I have found the more I use the focuser back and forth, the greater the tendency there is to loosen the small screws that attach the focuser to the OTA, and when those screws loosen up, I get binding, and the focuser has to be detached, mounting screws reattached. So this is not a small thing, and it's not going to stop me, frankly, from trying out the overshoot method of backlash compensation. But it is something to think about and realize that that's the path you're going down if you choose the overshoot method of compensation. So let's look at an example of what the overshoot method does. This is a very, obviously, simplified schematic of a rack and pinion system. In this case, we'll assume that the sensor is attached to the rack, and any counterclockwise motion of the pinion, where the gears, as you can see here, are already in contact, counterclockwise motion is going to move the rack to the left, which means the sensor will move inward. Consequently, or conversely, I should say, any clockwise rotation of the pinion is going to cause the gears to lose contact on this face, and for this gear tooth to ultimately engage on this gear tooth on the other side. This gap is what is the backlash that we're talking about. Until this gear tooth touches this gear tooth, you're not actually influencing the motion of the rack at all, and therefore you're not moving the sensor outward at all. So the outward motion has to use up this backlash range before you start moving the sensor out. Now, in this case, I'm going to use the example that I measured for my Celestron focuser and say that the actual focuser backlash is equal to 20 steps. So in other words, it takes 20 steps of clockwise motion of this pinion to rotate in order for this edge of the tooth to engage with this edge of the tooth of the rack. Second thing is, we're going to say, again, using the overshoot method, we need to to not just compensate for the backlash of 20 steps. We want to make sure that we've compensated for the actual backlash. So I'm going to overestimate what I think the actual backlash is and just call a large step 30 steps instead of 20. So I just want to make sure that whatever steps I'm using for the overshoot method here, they're larger than the actual number of steps of backlash. The gears are always engaged for one direction, either for inward motion or outward motion. In the application that I'm going to show you where we can take this method and try to apply it to Astrophotography tool, then we need to make sure that the gears are always engaged for inward movement. When we decide to execute a focuser motion on the inward direction, there is no backlash because the gears are already and always engaged in this scenario. Now, when we command focuser to move in the outward direction by, let's use an example of 10 steps, then the focuser needs to move by the 10 steps that we command it plus the large step of 30 steps, so it's going to move a total of 40 steps in the other direction. At least the pinion is going to rotate in the clockwise direction by 40 steps. And finally, when it's done with that, it's going to move back by 30 steps. Again, this 30 steps is the constant that's coming from this large step that we define to remove the backlash and the overshoot, leaving us ultimately with the 10 steps of backward movement that we actually want. Now, in this example, this rack schematic here represents the OTA, and just as a number, we'll call that it's at a position of 3,000. Likewise, this represents the pinion represents the focuser. We'll call that a number of 3,000 just for the sake of simplicity. And as we go through this example, the pseudo animation, you'll see these numbers actually change. So the numbers associated with the pinion are going to change more rapidly, more often than the numbers with the OTA, because once we start getting into the backlash zone, it's only the pinion that's moving, not the rack. Okay, so let's go on to our scenario here. Again, we're starting with the assumption that the gears are engaged for inward movement and nothing is moving at this stage. All right, now we issue a command to tell the focuser to move the sensor outward by 10 steps. We're changing the focuser's position, that is this guy's position, but we want to change the sensor's position. That's what matters in terms of focus. So in this example, we're going to move outward by 10 steps, which means we need to deal with this backlash here. Now, I just made a little step move you saw it go back. Notice I made the move here. All right, so the gears are not engaged at this stage. This gear tooth has separated from this gear tooth. Now the focuser has moved by 3 steps in the outward direction, but the OTA side of the focuser, the rack, has not. So the sensor has not moved at all. As I continue this movement, again, we're at 6 steps outward, no movement of the sensor on the OTA, once again, and we keep going until finally the gear tooth over here engages with the gear tooth on the rack, and nothing has moved yet on the rack side or the sensor side, so we're still at the same position we've always been. The focuser, in fact, has moved to 20 steps. That's the backlash. So the focuser has moved 20 steps inward, and yet the sensor has not moved at all because we had to use up that gap between the gears in order to engage the gear on the rack and start moving it outwards. Now, we'll continue moving the focuser outwards so that now we're finally starting to move the sensor. And as you can see, we're at 30-23 on the focuser, and we finally picked up some movement on the OTA. We continue doing this until we have completed our large step of 30 steps is complete, but we still haven't done our 10 steps that we requested. Now we've got to execute the 10 steps that we ultimately commanded. This is just the large step. So we continue on for another 10 steps, and now the gears are still engaged for outward movement, but they're stationary because we've completed the 40-step outward movement. Notice that the focuser has moved the 40 steps. The OTA side of the focuser, the sensor, has only moved 20 steps outward. But we're not done. Now we need to do the move back inward by that 30 steps. Here we are. Now notice that we moved one step, so we moved away. Now this gear tooth is no longer, this gear side on the pinion is no longer in contact with the rack, but we're continuing to move back in, so the focuser number is changing, but the OTA side of the focuser is not. We continue moving back until finally the gear teeth touch for the rack and the pinion, but now on the inward side of motion. So we've completed covered the backlash phase of the motion, but now we still have that extra 10 steps that we put in, and that's when we finally achieve our objective. Now, if we do another outward movement, it'll just repeat the same process that we just went through. If we need to move inward by 5 steps, no problem, because these gears are already engaged, so we would decrease this by 5, and the focuser would decrease by 5. How do we do this in Astrophotography tool? Well, theoretically, we can go into the settings section and the scope and focuser tab within the settings section of Astrophotography tool. And what you would need to do is to set your focuser backlash to 0 for both inward and outward motion, and then come down and click the check mark for make a final inwards move and enter into this box that large move. So whatever you think your focuser backlash is, take that number and add on something extra to make sure that it's larger than your actual backlash. As an optional part of this procedure, at the beginning of your imaging session, when you first turn everything on, you might want to execute a one-step outward motion at the start, because what that will do is will execute that example that we just did for one focuser step, but ultimately it's going to leave you with a pinion that is bearing on the rack for inward motion. So in other words, there won't be any backlash for the inward direction. Now, this is not a critical thing. You can choose to do this or not, and I think everything will ultimately work out just fine. This is what it looks like for Nina version 1.10.081, and in particular we're talking about this section down here. Now, one difference between APT and Nina is you can't have the focuser electronically connected, so you can start Nina but don't connect the focuser. Otherwise, this area is going to be grayed out. That's not true with APT. You can make these changes with the focuser connected within APT. Before you do these settings, make sure the focuser is not connected. Pull this drop-down box. It'll say either absolute or overshoot. We're talking about the overshoot method, so select the overshoot. And then for backlash in or out, if you want to replicate what Nina is doing, where the engagement of the gears is always set for inward motion with no backlash, and it compensates for backlash on the outward motion, then you use these settings: a 0 for the inward backlash, and in our case, this example, use the 30 or large step increment for the outward backlash. You may want to do opposite. You may want to have a setting for the gears bearing so that the outward motion is the preferred direction, or the no backlash direction, and that you're compensating for backlash for inward moves. And in that case, you just reverse these two numbers and put 30 here and 0 here. But these are the two settings you would use for APT and for Nina in order to implement the overshoot focuser backlash compensation method. I think the overshoot method is just brilliant, and I'm really kind of ticked off with myself for not thinking of it without first hearing about it. But the overshoot method has been in Sequence Generator Pro, and for those of you using that tool, this is no surprise. But it's just recently been implemented in Nina, which is how I first heard about it. And the key advantage of the overshoot method is it does not require an accurate measure of focuser backlash, but yet will, if you implement it properly, will take care of the backlash, no problem. And that's what our ultimate objective is. You just need to have some method of estimating what that backlash actually is. Now, the overshoot method, I think, can be emulated within Astrophotography tool by setting the in-out focuser backlash values to 0 and checking the make final inwards move box using a number of focuser steps that are greater than the actual backlash. So that large number we would use in Nina is the same number we would use here. And I think this will emulate the overshoot method. The only difference between Nina and APT is that you don't have a choice within APT whether the backlash is on the inward side or the outward side of motion, it has to be on the outward side of motion so that you're always in contact for inward motion. I think this is very interesting, and even though there are some potential disadvantages of more focus or motion, which can be problematic, I'm going to give it a shot anyway, and I suggest you guys give it a shot and let me know what you think. All right, guys, that's all. I got to go run and water my scope, so I'll talk to you later.